Hi, this is Lisa Knight, and I'm going to go over um, Lab 2, Part 1, the acceleration of dry ice pucks. So in this lab, you're going to choose a ramp, and an ice puck is going to slide down it. You're going to turn on your video analysis tools, and you're going to rotate the ruler so it's along the track. And what I did is I put the 0 right next to the back of the puck at the beginning of the video. Then I advanced it out until I could really see it start accelerating, getting faster and faster appreciably. And I turned on the clock and put it where I could see it really well. And I just kind of kept stepping it up. And it turns out that I stepped it up. I started at about 1 second. And I just read off how many centimeters it had traveled. And I did that for every 0.1 seconds so I could get a good value. And I just read it off and I just plotted that data. And I called this the time column and I called this the position column and I put in my variables. So my variable, my units would be centimeters and for that one, and my seconds would be for time. So I don't have to even put them in parentheses. I can just put them there. And the variable for time is a t, and the variable for position is a x or y, whatever you want to call it. And then I plotted. I went over here to curve fits, and I said that I wanted to do, well, first of all, I didn't do that yet. I went over here and I chose position on this axis, and I chose time, excuse me, on this axis. And when I look at it, looks like it could be a straight line, but if I really look at it, it might not be. So notice that the straight line's not really going through it. Turns out that when things are accelerating, and you should have learned this in your book, the position graph is a quadratic. So I did a quadratic fit to it because I was a good physics student. And actually, that goes through most of the points, and it's a better fit. And I see that my quadratic is equal to y equals ax squared plus bx plus c. And it tells me that this coefficient here is 109 and b is negative 134. That would be its initial speed. And c is its initial position on the track. Okay? And so the next thing they want you to do is that they want you to talk about what the shape of that is. So it's tempting to say that that's a line, but when you fit a line to it, it doesn't go through most of the points. So really in motion, you're in position graphs that we deal with are either lines or they're parabolas, quadratics. So those are the two functions that you should be looking at. Notice that the RMSE is close to 1, so that means it's a pretty good fit. All right, and the next part of this is to linearize the data. So one method to look at the relationship between two variables like position and time would be to take a curve like this quadratic, y equals ax squared, and to flatten it out. So right now it's a curve because you're plotting y as a function of just time. But if I plotted y as a function of x squared, of time squared, on the x-axis, then it would flatten out. And so what they want you to do is they go through the steps of telling you how to create a new column. So to create a new column, you just click on the 3 dots and you say insert column to the right. And then the new column that you're going to want to do is you don't want to have time on the x-axis. You want to have time squared on the x-axis. So I went to change column formula. And I just put t times t, or I went time, and then the times, asterisk, and then time, and I pressed submit. And I just wrote my formula in there, and it did the math for me. My units are going to be seconds squared, and my variable is going to be time squared. And so now they want to graph that, and if that is a quadratic relationship between between x and t, then when I do a position versus time squared graph, it'll flatten out. So I'm just going to come over here to my column, and instead of choosing time, I'm going to choose time squared. And it still has a parabola, but you see the parabola is not fitting it very well now. RMSE is 2. You want it to be close to 1. And I'm going to change my curve fit to a line now. And it does. It fits it very well. So the slope here is in centimeters per second squared. That's our acceleration. And that's our average acceleration. So as you go through this, you're just verifying that that is indeed a quadratic relationship. Then they want you to write the equation out. So I just wrote the equation that the computer gave me, which was y equals 61.33 plus negative 45.7. And then they want you to describe what the equation is. They want you to tell what the units of it are and what it means. And then they want you to tell what the x-intercept is. So the x-intercept, so this is a position equation. The x-intercept would be where it was on the x-axis. So I didn't write that in my lab, but I will. Now, if you want to go further, you can make a velocity graph and go through the same thing, but that was only optional, and I'm not going to go over the answers here.